Swayam Prabha. Digital India. Educated India.
Hello everybody. Today I am starting module 5 of the course Plates and Shells. So, today is the first lecture of the module 5, and in this module actually we will start the formulation of the plate problem using some approximate method. Approximate methods gives satisfactory result if it is used with caution, and this result can be acceptable in practical application. Now, let us see what are the different approximate method that we want to use in plate problem. Okay. So, today we will discuss the first the introduction to various approximate methods for the plate, expression for the strain energy for the plate in Cartesian and polar coordinate system for axisymmetrical cases. Now, first I will enlist different types of approximate method, and then I will focus the first one which requires the strain energy expression of the plate. Then I will discuss the energy approach, that is called the variational methods and its application. Now, based on the energy principle, Rayleigh's approximate method is very popular in case of the mechanics problem encountered not only in plate, in other field also. So, that Rayleigh's method will be discussed with necessary derivations, and then applications to beam and simply supported plate problem. First, I will show how this method can be applied to a beam, because plate is an extension of the beam theory. So, if you know the application, if you understand the Rayleigh's method and its use in the beam problems, then it will be easier for you or the users to apply this in the two dimensional problem like plate. Okay. So, first let us see why we need the approximate method. Okay. The exact solution of the plate problems are limited. Why it is limited? Because the deflection that we have found is valid for some cases a simple boundary condition, that is a simply supported condition. You have seen that the plate deflections were expressed in terms of double trigonometrical series, which satisfies the simply supported boundary condition along the four edges of a rectangular plate, or in case of a rectangular plate where the two opposite edges are simply supported, then we use the Levy's solution, Levy's series, that is a single trigonometrical series, and then we could find the exact solution of the differential equation. But this type of problem is not always common. For example, we may have a plate or say for example, a slab on which three edges are fixed and one edge is free. So, in that case it neither falls into the Navier's category or Levy's boundary category. So, in that case we have to take some other methods. So, therefore, the need of approximate method arises, and also you have seen that the loading condition also plays an important role, because if the loading is unsymmetrical, then we could not find the solutions of the circular plate using the axisymmetrical condition for the differential equation. So, that things are observed, and therefore, some techniques are required to be developed for solving problems which is different from the condition that were encountered in case of exact methods. Okay. Exact method of course gives you the exact result, that means error is negligible, but again it depends on how you formulate the problem. For example, the truncation error, that is one important thing in you have seen in case of this series solution, where you can truncate the series say at 3 terms or 5 terms or even in 1 term. So, in that case you have seen that the solution, the answer differs. Difference may be negligible, but this the truncation error is also common. So, therefore, need arises to solve or to find an approximate method which can take the errors in boundary conditions or boundary conditions that are different from the ideal situation, and loading is also different in ideal situation. Okay. So, accuracy of the results in approximate method is very important factor, because you have to use the approximate method with caution. So, what are the precautions that you have to take? One precaution is that input data should be as realistic as possible. So, incorrect input data such as material properties that we require in plate problem, which are usually the modulus of elasticity of the material and the Poisson ratio of the material. So, for steel plate that the modulus of elasticity of Poisson ratios are almost homogeneous quantity, but concrete is a heterogeneous material, and when this concrete slab is cast and the grade of concrete may be specified something, but in real situation when the concrete strength is tested, it may not reflect the actual theoretical strength that is assumed in case of mixed design. So, therefore, the need arises to develop a approximate method which can take care of this incorrect input data and the minimize the error. Actual boundary conditions can never be incorporated in the theoretical solutions. So, that is also another source of error in the approximate method, or you can tell it this is a major source in case of these analytical problems. Okay. Then calculation errors are also involved. These errors are actually due to incorrect assumptions, that certain assumptions are made that deflection is small, and then say for example, these in plane forces are neglected in case of thin plate theory, but and shear deformation is neglected, but even say some cases the thickness is required to be increased. So, therefore, the error crept up, because the thin plate theory does not include the shear deformation in the equilibrium equations. So, therefore, the necessity arises to use the approximate method to handle the complicated situations. The different approximate method that are used in plate problems are Rayleigh's method, Galerkin method, and finite difference method, and lastly finite element method. In this course, we will touch upon these first 3 methods, that is Rayleigh's method, Galerkin method and finite difference method. Finite element method is outside the purview of this course. So, first 2 methods that you are seeing, that Rayleigh's method and Galerkin method have its origin from the energy principles. Then third method is finite difference method. In finite difference method, the main thing is that we have the differential equation for the physical problem, whether it is plate or beam, whatever may be, beam bending or buckling of column, or for example, plate bending, buckling of plates, vibration. Many physical problems are there which are represented or by differential equation, differential equations of equilibrium, static equilibrium, or differential equations of equation of motion. Okay. So, in that case, when the boundary condition and loading is such that exact solution of the differential equation is not possible, then we express the differential equation in finite difference form. So, we write this in finite difference form. As a result, differential equation could be converted in a algebraic equation. So, you will appreciate that it is easier to solve a algebraic equation compared to differential equation. So, therefore, finite difference method ultimately requires the solution of algebraic equation instead of differential equation. The other two methods, the 1 and 2 that I have listed here, one is Rayleigh's method and another is Galerkin method. These also in the final step of formulation, you will get that these equations to be solved for unknown parameter are all linear simultaneous equation. So, in all the cases we require to solve only the linear simultaneous equation for the plate problem. So, therefore, it becomes easier for the analyst to use this method for such problems which could not be handled by exact solution method approach. Finite element method, of course, it is a different approach, and it also owes its has its source from the energy. Energy principle can be used to formulate the finite element method also. Okay. Now, let us see the first one, the Rayleigh's method in detail. Okay. This method is based on the energy principle in mechanics. Therefore, it is necessary first to know the strain energy of the plate. In this course, we will consider the strain energy stored in the plate is mainly contributed by the bending and twisting moment. That means, the contribution of in plane forces and contribution of shear forces towards the bending strain energy are neglected. So, that is very important thing, only strain energy due to bending moment and twisting moment has to be considered in the formulation of the problem in this course. However, the Rayleigh's method does not restrict that one has to use only the strain energy for expression for bending moment and twisting moment. One can include the shearing deformation as well as in plane forces also in the strain energy expressions. Okay. Now, let us see strain energy expression in the for the bending of plate. Okay. So, here you are seeing that a plate which has a dimension a b, and in that case we take an element of the plate whose length is d x along the x direction and dy along the y direction. So, moment you are seeing m x is the bending moment along the x axis, and on the opposite side the m x plus indicates that m x plus increment of the moment. Increment of the moment is d m x del m x by del x into d x along the x direction. Similarly, in that case m y is the bending moment along the y direction. In the opposite edges the bending moment will be m y plus. What does it mean? M y plus means m y plus del m y by del y into d y. So, these are the increments. So, similar meaning can be given on the m x y and m x y plus. Okay. So, plus quantity indicates the incremental quantity. Okay. Now, let us see, in general we know that work done by the couple m is any couple for undergoing a rotation through an angle theta. You can see that the strain energy is nothing but by the work done by the external force which is stored as a strain energy. So, in that case suppose a body is deformed by a force, and here of course, the body is undergoing the rotation due to application of bending moment. So, due to resistance of the this bending moment, applied bending moment, that is the we call it moment of resistance, the energy is stored in the plate. So, this energy if we want to formulate it, we will assume that the load is applied gradually, and therefore, the work done by the couple will be half m into d theta. That is the first initially, say for example, the it is a 0 couple and gradually increased, and then when the average value is taken half m and within a angle rotational increment of d theta, we take the strain energy expression as d w equal to half m d theta. d w is nothing but the work done by the couple, which is stored as a strain energy. Okay. Now, let us see the d theta. Here if you see in this figure that m x is the bending moment along the x direction, and there you will find that m x plus, that is the bending moment with increment. So, m x plus d m x by del m x by del y into d x. So, that is the bending moment on the opposite edges. Now, similar thing happens, suppose at this point the slope is del w by del x. In the opposite edges, the slope will be del w by del x plus increment of slope. So, increment of slope is del by del x into del w by del x into dx. So, increment of slope will be del square w by del x square into dx. Okay. So, with that condition, we can now say the work done by the bending moment or couple is half the moment into change of angle in elemental length. Okay. So, knowing this fact, now we can write the strain energy due to m x is del u 1, say this part is u 1. Contribution towards the strain energy due to bending moment along x axis is u 1. So, del u 1 we can write half m x dy. Why it is m x dy? Because m x is acting along the edge whose length is dy. So, therefore, m x dy is the total bending moment along this edge, because m x, m y etcetera are considered to be quantity per unit length. Okay. So, within this small element we assume that the moment is uniformly distributed. So, this m x dy is the bending moment along this edge, and therefore, half m, this is the m into the change of the slope. So, change of the slope here we have seen that change of the slope, if it is del w by del x, here it will be del w by del x plus del by del x into del w by del x. So, naturally this quantity comes here. So, the minus sign is taken because this with the increase of deflection the slope value decreases, therefore, minus sign is taken in this expression. Strain energy due to m y is also written in a similar fashion, half m y dx, because m y is acting along the edge whose length is dx. So, half m y dx is the average moment acting on this edge multiplied by the change of the slope. So, that quantity is taken because here now slope is along the y direction. Okay. So, this is strain energy due to m y. Next, we consider the strain energy due to twisting moment. So, in general, work done due to twisting moment is given by d w equal to half twisting moment, whatever twisting moment is there, into change of twist angle. So, strain energy due to m x y now can be written with the above analogy that we have used for m x and m y. Half m x y dy is the twisting moment acting along this edge, along the edge which is parallel to y axis. So, then this change of twist angle that is taken here. So, this gives the strain energy due to m x y. Similarly, strain energy due to m y x on the other edge m y x can also be calculated using this relationship. Okay. So, then we have taken all the components of moment for calculating the strain energy. What are the components of moment? The mx in the x direction, my in the y direction, and the twisting moment mxy. Mxy equal to myx, and for this expression can be simplified. Okay. This the twisting moment expression, strain energy for the twisting moment expression can be simplified by taking mxy equal to myx. Okay. So, expression for total strain energy now becomes the summation of all components. So, what are the components? Let us see. du1 is one component, that is contributed by mx. du2 is another component, that is contributed by my. Then du3 is another component contributed by mxy, and lastly du4 is the part of the strain energy that is produced due to myx. Okay. So, adding all these component du equal to du1 plus du2 plus du3 plus du4, we get ultimately this minus half mx del square w by del x square plus my del square w by del y square plus 2 mxy del square w del x del y, and dx dy is coming. So, dx dy represents the area of the elemental length. So, actually this is, if you see, this quantity is the strain energy density, and when we want to find this total strain energy, we must integrate it over the domain of the plate. Now, let us express the strain energy in terms of deflection. Okay. Knowing that strain energy mx, my, mxy can be related to the deflection, that is the curvature in the x direction as well as y direction, and also mxy can be related to the twisting curvature, then we have this expression already derived in my earlier classes, mx equal to minus d bracket del square w by del x square plus mu into del square w by del y square. So, this is the bending moment expression along the x direction. Then my is equal to minus d del square w by del y square plus mu into del square w by del x square. mxy equal to minus d 1 minus mu del square w del x del y. So, substituting this value here mx, my and 2 mxy, whatever is there, we ultimately get this expression for the strain energy of an element in terms of deflection and its derivative, mainly the second derivative of the deflections. Okay. So, now you can see, after arranging this, the strain energy can be now written in terms of the derivative of the deflection. So, here you will get del square w by del x square is directly coming from here, and half term will be there. So, d by 2 will be there, and minus all these bending moment expressions have negative sign. So, ultimately the strain energy will be a positive quantity. So, this you are getting here, first term is the curvature square, curvature in the x direction, and this is squared up. So, this is the first term. Then second term is the curvature in the y direction, and also it is squared up. Then you are getting 2 into mu del square w del x square del square w del y square, and then other term which are related to the twisting curvature is here 2 into 1 minus mu into del square w del x del y whole square. So, you get this expression for the strain energy after substituting this in the strain energy expression, and this is the most useful expression for solving the plate problem, because the plate problem using the Rayleigh method or approximation or any other Galerkin method requires the first approximation of the deflection. So, therefore, this form of the strain energy is very convenient to be used for plate problem. Okay. Now, this expression can be written in another way. This expression now can be written in a very convenient form, and from where some physical interpretation can be done and the strain energy expression can be simplified for some cases. Okay. Now, here you can see if we add 2 into del square W del x square plus del square W del y square without Poisson ratio here in this expression, if I add this and then again subtract it to keep the expression same without affecting the expression. So, we add a quantity, what is the quantity? 2 del square W del x square into del square W by del y square. So, that quantity is added in this expression and then same quantity is subtracted. So, ultimately the equality is not affected. So, the same quantity, that is it is subtracted minus 2 del square W del x square del square W del y square is also added. Okay. So, then you can see if I take 3 terms del square W del x square whole square plus del square W del y square whole square plus another term that I added 2 into del square W del x square del square W del y square, these 3 terms can be combined and can be written in this form, say del square W by del x square plus del square W by del y square whole square. So, this is written in a compact form. Then the other term that remains, that is we subtracted, one term we added and another term is subtracted, the same term is subtracted. So, the term that is subtracted is again 2 into del square W del x square into del square W del y square. So, combining this term with this expression, now we can express the strain energy in this form. So, equation 8 is very useful for the problems that we will discuss, that we can neglect some terms to simplify the calculations. Okay. So, after knowing the strain energy expression in general for the plate in Cartesian coordinate system, now we can see that some plate has edges which are clamped. There are many plates which all edges are clamped. Okay. It is argued like that the plate whose all edges are clamped, then the term inside the second bracket in equation 8, the second term, actually the second term, the term inside the second bracket, this is the term inside the second bracket, can be ignored or it vanishes. The same simplification holds good for other boundary conditions for rectangular plate, provided that either W is 0 or slope is 0, where n represents outward normal to the boundary. That means, slope along the normal direction is 0 and W along the boundary is 0. So, that conditions are satisfied in case of plates whose all edges are clamped, and also other for simply supported edges. This condition also holds good because curvature is 0. So, therefore, we can take this expression as a simplified form, neglecting this quantity inside the second bracket. So, strain energy for the plate which has all the edges supported can be written as u is equal to d by 2 integration. Why the integration is required? Because this expression was only for element, one element. So, after integrating we get the strain energy for the entire plate, that is the entire domain we used to integrate 0 to n 0 to b are the limits of the plate. So, after simplification you can see the strain energy can be written as d by 2 integration 0 to a 0 to b bracket del square W del x square plus del square W del y square whole square. So, this is the expression of strain energy for the plate. Now, in case of say for example, a beam problem where D is flexural rigidity in case of plate, but in case of beam D may be replaced by E I, and the deflection in the other direction was ignored in case of the curvature in the other direction, this width direction is ignored in case of beam, or also in case of plate which are very long. That means, plate has length breadth ratio is very high, that means width is very small compared to length. In that case, the curvature in other directions, there is the, if the x direction is the longitudinal direction, curvature in the y direction can be neglected. So, in that case the bending moment the strain energy expression is also used after neglecting this curvature in the y direction. Okay. So, knowing the strain energy expression for the plate or any structural element, whether it is beam or other elements, then we can find the total potential of the system. Here I am mentioning plate because the course is focused on the plate only, but this term that I have written pi equal to u minus w can be used for any type of structural element also. So, capital pi is the symbol that is used here to denote the total potential of the plate. Okay. So, what is total potential? That is strain energy minus work done, W is the work done due to external loading. We are considering only static problem. So, the kinetic energy is not coming here, but when you consider the kinetic energy for analysis of vibration, then the total potential expression will also include the kinetic energy term. Now, for a rectangular plate that is supported along the 4 edges, the strain energy expression is this. If it is not supported along the 4 edges, that means say for example, one edge is free, then you cannot use this expression. Then you have to use the general expression with this term containing the Poisson ratio, 1 minus mu is the factor. But in case of plates where all edges are clamped or the plates are supported along all 4 edges, rectangular plate, such that W is 0 or the slope normal to the boundary n represents the outward normal to the boundary is 0, then we can use the simplified form of the strain energy. Okay. The W is the work done by externally applied load. If the plate is subjected to distributed loading say q x y, then W is nothing but the load multiplied by the deformation and it is integrated over the domain. Okay. Now, here we have not used the term half based on the reason that the deformation does not change during the application of the load, or the load does not change during the where the plate is undergoing the deformation. So, therefore, in case of W we have not used the factor half. Okay. So, on the similar argument from the basic principle, considering the radial moment and circumferential moment that I have used to formulate the strain energy or used to the bending moment and twisting moment are used to derive the strain energy of the rectangular plate. Now, for circular plate in axisymmetrical cases there will be no twisting moment. So, in that case this strain energy expression can be written after integrating over the domain, writing the strain energy expression for the element and then integrating over the domain, the strain energy expression becomes u equal to d by 2 integration 0 to 2 pi 0 to r. Then you can see this term d square w by dr square plus 1 by r dw by dr whole square minus 2 into 1 minus mu divided by r dw by dr d square w dr square into r dr d theta. Why r dr d theta? The r d theta is the length of a sector arc r d theta at a distance r, and dr is the width of the sector. So, area of the sector or element of the circular plate is r d theta into dr. So, this is the area of the element and this is the strain energy of the element, So, when it is multiplied by the area and it is integrated, we get the total strain energy of the circular plate. Now, you can see here that these functions W or its derivatives in case of axisymmetrical problem are not dependent on theta. That means, this W does not contain any theta. So, therefore, we can integrate this expression independently with respect to theta. As a result, the d theta integration from 0 to 2 pi is nothing but 2 pi. So, after that only integration with respect to r remains, and capital R is the radius of the circular plate. So, after performing integration with respect to theta, we get ultimately the final expression for the strain energy of the circular plate in axisymmetrical cases as equal to pi d 0 to r bracket d square w by dr square plus 1 by r dw by dr whole square minus 2 into 1 minus mu divided by r dw by dr d square w dr square r dr. Again, this simplification is possible when the boundary of the plate has either w is equal to 0 or dw by dn equal to 0, where n is the outward normal to the plate. Then second term in the above expression vanishes. Okay. So, therefore, in case of plate which has supported boundary, then we can write the strain energy expression for the plate as pi d 0 to r d square w dr square plus 1 by r dw by dr whole square r dr. Okay. Now, suppose we want to solve a problem of a plate which is having a fixed boundary, that is, it is fixed along the all edges. So, in that case it is not necessary to consider the second term, because the dw by dr slope becomes 0. So, in that case the second term can be used, the first term, that is the square term, will be used to calculate the strain energy of the plate. Okay. Now, based on the strain energy and total potential of the system, we now write that total potential equal to u minus w. Now, based on the energy principle and minimization of the energy total potential, it can be written that variation of pi equal to 0. That has immense significance in case of physical problems that are encountered in our engineering applications, because this single equation, that is this delta, represents the variation of the total potential is 0. This is possible because of minimum potential energy at the stable equilibrium configuration. So, if we write that del pi equal to 0, that means pi involved your strain energy and work done, which involves also the deflection expression. So, in case of formulating a problem, when we want to establish the equilibrium equations and we are not able to formulate the equilibrium equation from the force balance or Newton's law, then we can take the help of variational principle, which will give the same differential equation with ease in some cases. In some cases it may be complicated also, but problems which has complicated boundary and complicated loading conditions, in that case the variational principle, that is del pi equal to 0, that equation gives the yields the differential equation of the equilibrium as well as boundary condition. So, this equation simultaneously gives the differential equations of the equilibrium as well as boundary condition. So, I will explain one problem, the case how the differential equation is obtained using the variational principle and how the boundary conditions are known using the variational principle. Okay. So, let us see an application of the variational principle. Consider a long plate. I am taking a long plate, width is very less than length, whose flexural rigidity is d, resting on elastic subgrade whose modulus of subgrade reaction is k, and the subgrade is continuous. The plate is supported over the subgrade continuously, there was no break of this support. So, this condition may be used to idealize a road pavement, because road pavement is using rested on the subgrade, and you know that pavement is having a concrete slab in many cases. So, concrete slab acts like a plate, very long plate resting on the elastic subgrade. Now, elastic subgrade are acting also like a spring, that it will produce a upward reaction to the deflection of the plate. So, the spring force that will be produced in the subgrade will be upward, and it will resist the downward load or the load acting on the plate. That means, it will reduce the deflection. So, here the elastic subgrade acts like a linear spring continuously distributed over the entire area. So, what we require? We require to find the differential equation of the system of this plate as well as boundary condition using the variational principle. Okay. So, to use the variational principle, the first thing is that we must know the strain energy expression of the plate. Without knowing the strain energy expression, you cannot proceed to use this variational principle. So, strain energy expression of the plate, because of this long plate, the curvature in the other direction is neglected, and then we write it d by 2 0 to L d square w dx square whole square dx. So, this is the strain energy of the long plate, okay, which is actually behaving like a beam. Then work done by the external load. What are the load on the plate? That is, suppose some distributed load is acting on the plate. Here we have taken a distributed load acting on the plate continuously along this plate, or it may have a discontinuous partial distribution also, does not matter. But in that case, we are taking that load is continuously distributed along the length of the plate. So, with the work done by the external load is q x w into d x. Then the work done by the distributed spring force due to subgrade reaction, the spring force is opposite to the displacement. So, therefore, work done by the spring force will be negative. Hence, we take that work done by the spring force as k w into w by 2 into dx. So, half I have taken outside, and then we have integrated over the length of the plate. So, this represents the work done by the spring force. Now, we write the total potential pi equal to u minus w. So, u is d by 2 0 to L d square w dx square whole square into dx minus w, and what is w? W we have got two components. So, first component is due to this distributed external load, and second component is due to spring reaction. So, we have written this first component was negative there, and it is now becoming positive, because minus w is there and work done due to distributed loading. Okay. In order to find out the differential equation and boundary condition, I told you that we have to take the variation of u. So, take the variation of u, delta u. Variation is a operator just like differentiation. So, this del u is, that means the quantity inside whatever u is there, u is d by 2 0 to L d square w dx square whole square, that has to be operated with the variational operator delta. So, small delta operation is done here. You can see that u quantity is this. So, if I operate this quantity with delta, that means like a differentiation, we take this, this will be 2 d square w dx square, and then the variation of this quantity. So, it is written based on this similar to the differentiation process. So, d square w dx square into delta d square w by dx square, that is the variation of this quantity, into dx is of course there, and it is integration is there 0 to L. Okay. Now, you can see this quantity has to be integrated. So, how it will be integrated? You see that this is one function and that is another function. So, we have to use the integration by product rule. Okay. So, if we use the integration by product rule, it is further written in this form before starting the process of integration. So, this the differential operator and this variational operator are interchanged. So, it is written as d by dx variation of this dw by dx. So, after writing this, the integration process has been started. So, the first integration is yielding this result, that is, if I follow the integration of products rule, then this first function into integration of the second function. So, integration of the second function is del dw by dx, and then I put the limit 0 to L. That means, this quantity has to be found out at the boundaries 0 to L, minus derivative of the first integral d cube w by dx cube into integral of the second function. So, integral of the second function, that is this, and in the next slide you will find that I have integrated this second function and again we are getting this. Okay. So, this is remaining as it is. Now, we are getting this term, and again this is integrated, having observed that this is again a product of two function. So, the integration by product rule is again followed, and we got here say d the first function into integration of the second function. So, how it is done? That differential operator d by dx and variation operator are interchanged, and therefore, we are getting after integration delta w, and we put the limit to evaluate this quantity at the boundary. Then minus, and minus minus plus sign will be there, then d is there already, derivative of this term. So, d to the power 4 w divided by dx 4, the fourth derivative is coming, and then integration of this del w del x. Okay. So, we arrived up to this. So, du is completed, del u is completed, then variation of work done is calculated, del w equal to q x del w dx, and it is a very simple thing, you can say half k w square. So, when it is operated with delta, it becomes k w into del w, and dx is already there in the integration. Okay. So, according to the variational principle, we now write delta pi equal to 0. Now, substituting the component of delta pi is obtained as del u minus del w. So, substituting this all these component that we have evaluated in the earlier process, we now write del pi equal to this quantity equal to 0. Okay. So, you are getting here the quantity that have to be evaluated at the boundaries, here also the quantity that have to be evaluated in the boundary, and here there is one integral. Okay. Now, the right hand side is 0, that means, here we now know that del w is not 0, it is arbitrary quantity, it is arbitrary virtual displacement which is not 0. So, it indicates that the term inside the second bracket should be 0 and other the boundary quantities should be 0. So, based on that we can now write this first quantity is this, we can write this, second quantity is this. So, we write this is equal to 0, and third is the quantity inside the integral, and this is also equated to 0. So, the one that is the last expression that I have written, it gives the differential equation of equilibrium of the problem, and other two equations that I have written above is nothing but quantities related to the boundary values. Okay. Now, several combination of boundaries values are possible. Let us see. So, from the first equation we can now see that either this is 0 or this is 0. Okay. Product of two quantities are 0 is there. So, therefore, this is 0 or this is 0. Second boundary condition also yields like that, and third equation yields the governing differential equation. So, taking different combinations of these boundary values, we can now interpret physically the boundary conditions. The combinations of this in pairs gives the physical boundary conditions at the ends x is equal to 0 and x is equal to L. So, x is equal to 0, now one combination is w is equal to 0, dw by dx is equal to 0. So, that combination gives clamped edge, clamped end, and another combination may be w is equal to 0, d square w by dx square equal to 0. This combination gives hinged end or pinned end or simply supported end. Then the third combination, the d square w by dx square equal to 0 and d cube w dx cube equal to 0. So, that indicates this is the bending moment and this is the shear is 0. So, it is for the free end. So, in this way we have seen that use of variational principle by with the knowledge of strain energy expressions and the work done by the external load, we can arrive at the differential equations and boundary conditions for the physical problem. Okay. Now, let us derive the Rayleigh method. In the Rayleigh method, we shall assume that W, the deflection, is a function, a continuous function of x and y. Okay. So, we shall assume that W x y is a 1 f 1 x y, a 2 plus a 2 f 2 x y plus a 3 f 3 x y, like that we can take n number of terms. So, when f 1 f 2 f n are assumed function which satisfy boundary condition, that is most important thing. So, these functions are taken in such a way that boundary conditions are satisfied. There may be displacement boundary condition which are imposed on displacement and slopes, but there may be also the force boundary condition which may be applied to the shear force and bending moment. So, that means or twisting moment. So, in that case the f 1, f 2, f 3 etcetera to be chosen in such a way that the boundary conditions are satisfied. Now, in many problems it is difficult to satisfy the force boundary condition. So, we get naturally the errors in the result, final result, but deflection boundary conditions are in most cases it is satisfied, and if both the conditions are satisfied, then we get the exact results for the problem. Okay. So, how it is derived Rayleigh's method? We know the total potential pi, and total potential, when you know that total potential contains the strain energy as well as work done, which are also dependent on the displacement as well as its derivatives. So, therefore, this total energy total potential pi are also functions of the unknown constant a 1, a 2, a 3 etcetera. Okay. So, therefore, this using the chain rule of partial differentiation, we can now express delta pi equal to del pi by del a 1. Mind that this is the partial differentiation, but this is the variational quantity into del a 1 plus del pi by del a 2 del a 2 plus, like that it will go up to nth terms. Now, where del a 1 delta a 1 delta a 2 etcetera are arbitrary and non-zero constants. So, we can now say that when del pi is 0, then these are not 0, delta a 1 delta a 2 delta a n are not 0. That means, for any general term, say del pi by del a n should be 0. So, this is the equation to be used in Rayleigh's formulation. Okay. So, what are the steps? Let us see. First step is assume deflection function. We have assumed the deflection function like that. Then obtain the expression for the strain energy of the plate u, find the work done due to external load W, find the total potential pi equal to u minus W. Then you see that pi equal to u minus W contains this a 1, a 2, a 3 in square form. because it is a energy expression, it is coming from energy expression pi, capital pi. So, therefore, it will contain the square of this quantity. Now, for any term, we are showing it for any term, and we have to carry out for all number of terms this derivative, that del pi by del 1 equal to 0, del pi by del a 2 equal to 0, like that. Now, the beauty of this method is that since the energy expressions are all square terms, quadratic terms, and then when we differentiate with respect to say a 1, a 2, which appears as a square quantity in the potential, total potential, then after differential equation it becomes a linear equations. So, that means we have to solve n number of linear simultaneous equation involving the unknown parameters a 1, a 2, etc. So, when a 1, a 2, a n etc. are known, we now know the deflection equation completely. That means, deflected surface is now given as W is equal to a 1 f 1 x y plus a 2 f 2 x y plus a 3 f 3 x y, like that up to nth term if you consider. Now, accuracy of this method can be increased if we properly select the displacement function such that it satisfy the boundary condition as close as possible, and also if we increase the number of terms, the accuracy, the truncation error will be reduced. So, let us see an example. First, consider a cantilever beam of length L, flexural rigidity E I. I have selected a problem of beams, so that you can understand the concept of this problem, and then you can apply to the plate problem. So, it carries a uniformly distributed load Q naught for the whole span. Now, we require to find the deflection of the beam using Rayleigh approximate method. So, first we use the two terms of this series, Rayleigh's deflected series, or we use a polynomial expression with two terms, the quadratic term and cubic term, to approximate the deflected line, elastic line of the beam. Now, once this is known, then we can calculate the slope of this curve as well as the curvature of the curve. So, after getting this quantity, that is the slope and curvature of this, we now calculate the strain energy due to bending of the beam. So, strain energy due to bending of the beam, now it will be E I by 2 0 to L d square W dx square whole square dx. So, after substituting the value of d square W by dx square from the previous expression and then performing the integration, we arrive at the expression for u as this E I by 2 4 a 1 square into L plus 12 a 1 a 2 L square plus 12 a 2 square into L cube. Work done by the external load is simply the Q naught is the uniformly distributed load into W x, because W is a function of x displacement, into dx integrated over the length of the beam, and then we get Q naught equal to a 1 L cube by 3 plus a 2 L to the power 4 divided by 4. So, this is the work done expression and this is the strain energy expression. So, total potential now we can calculate pi equal to u minus W, substituting u from the previous expression, this expression, the equation number 5, and work done from the equation number 6. We now write pi equal to u minus W as E I by 2 4 a 1 square L plus 12 a 1 a 2 L square plus 12 a 2 square L cube minus Q naught a 1 L cube by 3 plus a 2 L to the power 4 by 4. So, this is the pi. Now, we use the Rayleigh's equation. So, what is Rayleigh's equation? Del pi by del a 1 equal to 0, del pi by del a 2 equal to 0, del pi by del a 3 equal to 0, but since we have taken only two terms in the deflected line, because it is a beam problem. So, we call it line. So, we have to differentiate it with respect to a 1 and a 2 separately. So, first we differentiate with a 1 and then we get del pi by del 1 equal to this quantity 8 A1 L plus 12 A2 L square equal to 2 Q naught by E I L cube by 3. Then similarly, we differentiate del pi by del A2 and we get A1 plus 2 A2 L equal to Q naught L square by 24 E I. So, you can see the equation 8 and equation 9 contains two unknown quantities A1 and A2, and this can be solved easily, and after solving we get A1 as this and A2 equal to this. A1 equal to 5 Q naught L square divided by 24 E I and A2 equal to minus Q naught L divided by 12 E I. Substituting A1 and A2 in the expression for deflection that we assumed previously here, equation number 1 in this problem, substituting A1 and A2 and arranging this, we can now write the expression of deflection in terms of this Q naught L to the power 4 divided by 8 E I bracket 5 x square by 3 L square minus 2 by 3 x cube by L cube. Now, we have taken the origin at the fixed end of the beam and x is equal to L end is free. Okay. So, for the cantilever problem, we know the deflection in the free end. Deflection in the fixed end, of course, it is a 0, slope is also 0. So, the deflection at the free end, if we want to calculate, we put x is equal to L and then we can see that exact value is obtained. We know from the strength of material formula that W at the cantilever free end or tip will be Q naught L to the power 4 8 E I, where Q naught is the distributed loading in the cantilever, L is the length and E I is the rigidity, flexural rigidity. So, here by taking two terms in the deflection series or deflection polynomial, we have chosen a polynomial function, but it is not necessary to choose a polynomial function. A trigonometrical function can also be chosen. Now, this function is chosen because you can observe that this function satisfy the deflection at the fixed end and slope at the fixed end. Fixed end is 0 n. So, put x is equal to 0, deflection is 0. Again, if you differentiate it and put x is equal to 0, the slope is 0. So, slope and deflection at the fixed end is satisfied. So, therefore, this represents a possible deflection function of the equation. Okay. By following the Rayleigh's procedure, we now obtain the deflection surface after evaluating the unknown A1 and A2, and this expression shows that deflection is exactly obtained, there is no error in the deflection. However, if you calculate the bending moment, you will get some error, and shear force again you will get error. So, a comparison I will give in the next slide, that what is the error involved in calculation of bending moment and shear force. First, let us see the whether accuracy is increased by using one more terms in the deflection series. So, if I add another terms A 3 x to the power 4 in the previous deflected series, deflected expression, this is also a admissible function because it satisfies the boundary condition at the fixed end. Force boundary condition, we are not sure whether it will satisfy or not. So, at the first look it is observed that this function satisfies the boundary condition at the fixed end, because putting x is equal to 0, deflection we are getting 0, and derivative we evaluate here as 2 a 1 x plus 3 a 2 x square plus 4 a 3 x cube. Again, if we put x is equal to 0, we get deflection slope equal to 0. So, both deflection and slope boundary conditions are satisfied at the fixed end. So, this is a admissible function for the deflection. So, as usual we take the second derivative, and this result is used in the strain energy expression. U is equal to E I by 2 0 to L d square W dx square whole square dx. So, the second derivative is taken and then it is the strain energy is evaluated. So, after evaluating the strain energy, we get U is equal to E I by 2 4 A 1 square L plus 12 A1 A2 L square plus L3 L cube 12 A2 square plus 16 A1 A3 plus 36 A2 A3 L to the power 4 144 by 5 A3 square L to the power 5. Work done by the external load is calculated as this, because this is a very simple integration, no derivative of the W is involved. So, we calculate this quantity and then the total potential is obtained, and using Rayleigh's equation, because here 3 constants are involved, 3 terms are used in expressing the deflection. So, we use the partial derivative of del pi with respect to del A1, again del pi with by del A2 and del pi by del A3, and these 3 partial derivatives are evaluated and equated to 0. So, we get 3 linear equations involving A1, A2, A3. You can see these 3 linear equations are obtained. Using this any method, say for example, Cramer's rule is a possible method for solving the linear simultaneous equation. We now obtain A1, A2, A3. So, obtaining this A1, A2, A3, we now express the deflection. So, from this deflection equation, we can now obtain the slope, bending moment and shear force using the derivative of the deflection function. Now, here I have given a comparison for the cantilever problem. First, I have taken that this 2 terms expression in the polynomial of the deflection A1 x square plus A2 x cube. Now, percentage error in deflection I have calculated, you can also check it, it will be 0. Percentage error in slope is also 0. Percentage error in bending moment is 16.67, whereas percentage error in shear force is 50%. But when we increase one term of the deflected series, we get the percentage error in deflection, slope and percentage error in bending moment and shear force. Bending moment and shear force refers to the bending moment and shear force at the fixed end, because these fixed end moments are maximum, whereas the slope and deflection are referred to the free end, where the standard values are known. Standard values of deflection at the fixed free end is W q naught L to the power 4 divided by 8 E I, whereas slope at the free end is q naught L cube divided by 6 E I. So, comparing this result from the Rayleigh's method with the standard value, we can now compare the errors. So, you can see that if the deflection function is properly chosen to satisfy the boundary conditions and containing the sufficient number of terms, we can obtain the acceptable result. Now, we give a plate problem example. So, take a simply supported plate which conveniently expressed deflection is expressed by the double trigonometrical series, because you know that sin m pi x by a, sin n pi y by b. If these these terms are summed up to infinite number of in a infinite series, then it represents the deflection of a simply supported plate. That means, the plate having all edges are simply supported. Now, since the plate is supported along the all edges, we now take the expression for strain energy considering only the first 2 terms, because the terms with where the Poisson ratios are involved, that is neglected, because the deflection and slope normal to the boundary of the supported edge were taken 0 for the camped edge, and it is also true for the simply supported edge, because the curvature product of curvature is there. So, it becomes 0. So, therefore, we take u is equal to d by 2 integration 0 to a 0 to b del square w del x square plus del square w del y square whole square dx dy. And work done due to external load, if q naught is the uniformly distributed load over the plate, that q naught w x y dx dy. Okay. Now, substituting this expression here and integrating, you have to carry out the double integration, that strain energy due to bending of plate now becomes pi to the power 4 a b d divided by 8 summation m is equal to 1 to infinity, n is equal to 1 to infinity, and this term results m square by a square plus n square by b square whole square m n square. So, this is the strain energy of the plate, and the work done due to external loading is expressed in this form. Okay. 4 q naught a b divided by pi square summation m is equal to 1 3 odd number of terms will be there, as we have seen in case of Navier's method, and also for n odd number of terms will be there only contributing to the work done. So, therefore, we get this work done as some double summation a m n divided by m n. Now, calculate the potential pi is equal to u minus w, then apply the Rayleigh's method del pi by del a m n equal to 0. After applying this, we now arrive the value of a m n. You can see when the strain energy is this expression is differentiated with respect to a m n, we get here pi to the power 4 a b d divided by 4 and a m n will be there. So, here we get pi to the power 4 a b d divided by 4, other terms are there already, a m n is there, and if we differentiate this quantity with respect to a m n, then it will be 1. So, we are getting in the right hand side 4 q naught a b pi square and other terms m n will be there. So, when we compare the coefficient of the like term, this is the result. So, from where a m n is obtained as 16 q naught divided by pi to the power 6 d m n m square by a square plus n square by b square whole square. So, that thing is well known to us, because in Navier's method, when we solved the differential equation of the plate using the series double trigonometrical series, we got the same expression. So, that means, in that case the force boundary condition as well as geometrical boundary conditions are satisfied using the double trigonometrical series. So, therefore, it yields the exact solution. Even we are using the Rayleigh's method, but we are arriving at the exact solution of the differential equation of the plate. So, Rayleigh's methods are very powerful technique in solving the boundary value problems in physical in mechanics or mathematical physics, and conveniently it is used for the plate problem of different nature. Let us see let us summarize the today's lecture. In this lecture, we have introduced various approximate methods for solving plate problem. The detailed discussions was done for the use of variational principle, and an illustration was given to obtain the governing differential equation and boundary conditions. Then Rayleigh's approximation method was formulated and illustrated with the example of beams and plates. Thank you very much.